So I will give you the student teacher version as well. Okay, please download the new PowerPoint slides. Chapter 10, Noise Pollution 2. And Chapter 12, Hazardous Waste Management. Two and one. Okay, please also go download Chapter 12, Hazardous Waste Management 1 and 2. And I give you teacher versions. That'll save you some time to take notes. Okay, let's get started. Okay, let's start from this page. Okay, so this is about this is so-called the loudness label. Oh, I'm sorry. Okay, so you didn't see anything. Oh, I'm sorry about it. Okay, so please go Moodle and download the files. Okay, please go Moodle and download the files. Okay, so we're gonna start with this page, the loudness label. The loudness label, and the loudness label measures in phones. So measure in phone. So measure. So the loudness label measure in phone. Measuring phone. Okay? And this figure show you the ear loudness contour. Okay, this is so-called the ear loudness contour. So this show you the sound pressure label. Sound pressure label here. The y-axis is sound pressure labels. Need a different frequency. Need a different frequency. So the x-axis is frequency. Need a different frequency. So the sound are perceived as equally loud by humans. Okay? For example, like so, for example, like here, the phones is equal to the sound pressure label in decibel for the bass, right? In decibels, and frequency equals 1K hertz. Okay? The phone is equal to the sound pressure level in decibel, and frequency equals 1 kilohertz. That means 60 phones. For example, like 60 phones equal 60 dB. 60 phones equals 60 dB. Sound pressure level at frequency 1 kilohertz. Okay, 60 phone equals 60 decibels. 60 decibels at 1 kilohertz. So for example like this. So 60 go here and count down. You see that? Okay? Everyone gets that? So this equals 1,000, right? So 60 phones equals 60 decibels. Sound pressure level at 1,000 hertz. Okay? So this is the unit. This is phone is the unit, as I said. The loudness level measured in phone. The unit of measurements of loudness level, we call this phone. We call this phone. Okay? So, we humans do not hear all the frequency equal well. Okay? We are more sensitive. Okay, here. This is what I mentioned here. We are more sensitive. We human beings, we are more sensitive around 3.5 to 4 kilohertz. Okay? So it's something around here, something around what I circled here. Okay, we human beings do not hear all the frequency equal well. Everyone understand? We are very sensitive. Okay, at the frequency from 3.5 to 4 kilohertz. This is what I circled here. So this is what I circled here. This is sensitive to humans hearing. So this range, okay, this range from 3.5 to 4 kilohertz is very sensitive to humans' ears, humans' hearings. Okay, so what does that mean? That means the sound in this range need less sound pressure. Okay, what does this mean? This means, let me write this one down. That means sounds in this range, 3.5 to 4, okay, need less sound pressure to be here as high. Let's write this one down. Okay? And also from these figures, from this PowerPoint slide, you understand only at 1,000 kilohertz. Oh, sorry, only at 1,000 hertz or 1 kilohertz. Okay, the phone equals dB. Okay, so the loudness So the loudness is not equal to dB for all the frequency. This is nothing you can do there. So by adjusting frequency, you can adjust the loudness. Understand? Okay? The loudness form, okay, measuring form. The loudness measuring form, okay, is not equal the decibel sound pressures label for all frequencies. Okay, everyone understand this? If you understand previous learning, this is very important. Otherwise, I can skip this. Okay. So here's I describe one thing: loudness level form. Okay, loudness level form, and sound pressure decibel. They are only equal at 1,000 hertz. Okay. So for example, like this. If you just use 500, right? So 500 is around here. Right? 500 is around here. Okay? So 500 hertz is around here. Okay? So 60 decibel become something less than, it's in between, let's say 57. So, at 500 hertz, 60, at 500 hertz, 60 decibel is pretty close to like 57 form. You know what I'm saying? Understand? So by adjusting frequency, you can adjust the loudness. Okay, I have another slide. Okay. So this slide also tell you about the loudness, but this is in songs. Okay. So song is also a unit. Sound is also a unit. Okay, the relation between sound and form is here. Okay, form equals 10 times sound plus 80 divided by 2. So it's pretty much like 30 forms. It's close to 0.5 sound. Okay, so one sound is close to, let me do this. One sound is close to 40 phones. Okay, 0.5 sounds is close to 30 phones. Okay, just another unit for loudness. Okay, just another unit for loudness. But normally, what's the difference? Normally, phone. We use phone to measure the loudness level. We use phone to measure the loudness level. However, we use sound to measure how loud humans actually Feel the sound. Feel the sound. Yes. Okay? Besides the convergence, one song equals 40 phones. Normally, we use phone to measure the loudness levels, like this, right? From the street, from the machines. And we use song. Normally, we use song to measure how loud humans actually feels or actually hears the sound. Okay? So, derived from the physiological test, where humans judge the sound to be twice as loud. Okay? So, a sound is close to 40 phones. Okay? And next slide, I would like to talk about the frequency weighting network. This is also described in the textbook. Okay, this is also described in the textbook. This is how I going to test in the exam, in the final exam. Okay? So, frequency weighting networks. So, as I just mentioned previously, right? Human ears do not hear all frequency equally, right? 人类的耳朵没办法听到每一种频率是相同的。Human ear do not hear all frequency equally. So we can use machine. So this kind of machine is called sound level meter. So we can use a machine, we can use a device called sound level meter. This kind of sound level meters they're gonna use electronic filters to imitate human hearing. Okay, we use a device. This kind of device is called sound level meter. Sound level meter uses electronic filter to imitate 模仿 to imitate humans hearing. Okay? And this okay? And these filters, those electronic filters is called here. It's called frequency weighting networks. Understand? Everyone? Sound level meter use electronic filter to imitate human hearing. And this electronic filter, this filter is called frequency weighting networks. Okay? So frequency weighting networks are electronic filter circuits built to match, right? To imitate, to match humans' ears frequency response at different sound intensity. Okay? And there are three kinds of filter. 有三种滤器. There are three kinds of filter. A, B, C. So there are three kinds of filter. A, B, C. Understand? So far so good? This part is kind of difficult. So far so good, everyone? Okay. There are three kinds of vowel, A, B, C. Okay. So let's talk about A first. So we call this, actually we call this A vowel. Okay, what A vowel do? What A vowel does? A vowel reduce very low frequency. I just read FS frequency, okay? Okay, especially below 50 hertz. 500 hertz, sorry. So, A vowelings strongly reduces very low frequency, especially below 500 hertz. Okay, we human beings cannot hear them. So it's commonly, so what kind of noise? Okay, below 5, so for example like environmental. Commonly used for environmental noise. Okay? Because it's close to humans hearing at normal sound levels. Okay, so for very low frequency, you can use a violin. Okay, which strongly reduce very low frequency, especially below 500 hertz. Very commonly used for environmental noise. Okay, that's A violins. Okay, and what we normally use is B filter, B violin. Okay, B violin is what we commonly use. So B violin try to reduce moderately. Okay, that means in the medium. Okay, not too low, not too high, in the medium. Okay, so reduce moderately low frequencies. Commonly used. Okay, the last one is C violins. Try to reduce very loud sound. Very loud sounds and high frequency. And high frequency. Okay? So less of lower and higher frequency are filtered by C filter, C value. Okay, so F filters, very low frequency. Okay, very low, severely, a lot by F filter. Low frequency, okay, low frequency can also be filtered by B, can also be filtered by B frequency, B wavelengths or B filter. A little bit less, lower and higher, higher. Okay, the louds, also the loud sounds. And the loud sounds are filtered by C filter. Loud sounds, all bass notes. Loud sounds, all bass notes. Okay. Can I modify this? Reduce very loud sound and less of lower and higher frequency. Okay? I would like to modify this. Very loud sounds, reduce very loud sounds and less of lower, is also able to reduce lower and higher frequencies. Okay? So everyone okay? Fish? So very low frequency filtered by A, low frequency filtered by B, less of lower and higher and loud sound and bass noise filters by C. Okay, so this graph shows you how much filter reduce different frequency. Okay, this slide shows you how much filter reduce frequency. So at low frequency, you see that? At low frequency, okay, such as at low frequency, the A filters, you see that L filters works, right? And in the middles, okay, B filters works. C is good for high frequency. C is good for higher frequency. Okay? Everyone understand? Okay? So this is we call this contour. Okay, contour filters. So this F welding removes a lot of low frequency. Okay, this F removes a lot of low frequency. Okay, especially bass. Okay. So for example, like a low frequency noise. Okay, low frequency noise such as deep bass or rumblings may be higher, may have a higher decibel values, but human may not hear it very strongly. Okay, human may not hear it very strongly. Then we can use a filter to reduce it. Okay, we can use a filter to reduce it. that's the reason this is very good. So A filter is very good for environmental noise. So air filter, air volume filter is very good for environmental noise. So B violins, okay, is something between A and C, right? So remove the low frequency. Okay, but not as strong as A. So it's designed for, so it's good for medium loud sound. Okay, and we use this. Okay, this is what we commonly use. Good for medium loud sound. Okay. Okay, I'm sorry, less commonly used. Because it is medium. I'm sorry, not commonly used. Less commonly used. Rarely used. Less common 少用 less commonly used. Good for medium sound. Okay. Good for medium loud sound. So, but medium loud sound actually you don't need to reduce it, right? So, rarely used. Rarely used. Okay, less commonly. Not commonly, I'm sorry. Rarely used. Understand, student? Less commonly used. 很少用，因为重度的声音你不用过滤嘛。Understand? Because this is medium loud sound. Okay, it's good for medium loud sound, but you don't need to reduce medium loud sound, right? If you reduce medium loud sound, the sound will become too soft, right? So we rarely use, student, we rarely use, okay? We rarely use, I'm sorry. Good for medium loud sound, but rarely use. Understand? Less commonly. Less commonly, not commonly. Okay, the last one. Okay. Does not filter much. Okay. So that means just a little. Just very little. Just very little. Low and high. Not just high. Filter low and high. Okay, so good for very loud sound. So you can see that has been used for traffic noise survey, right? In noisy area. So good for very loud sound. Okay, let me finish this slide before we take a short break. Okay. So the filters. So we seldom use DBB, right? We seldom use DBB. So normally we use DBA and DBC. Okay, DBA and DBC. DBA use A violin scale. Of course, DBC use C violin scale. So dBA represent how human usually hear noise. dBA is used to represent, okay? dBA is used to represent how human usually hear the noise. And dBC, actually, dBC is closer to the real physical sound pressure level. Because we say it's good for measuring very loud sound, bass heavy sound, right? Bass heavy sound, and high to low frequency. Okay? So dBA adjusted to human hearing. So it's good for reducing environmental noise. And dBC almost flat response. Almost flat response like this. You see that? Almost flat response like this. Almost flat response. Okay? So it's good for the loud noise. Okay, good for the loud noise, bass heavy sound, less of low to high frequency. Everyone okay? Okay, let's take a 5-minute short break. So now it's 2:14. Please come back 2:20.